Good morning. In this section we will see the transmission line equation. So here this is the equivalent circuit of a transmission line, and here you can see inductance, resistance, capacitance and conductance, and all these parameters are multiplied with del Z. It's done to make L, R, C and G into absolute value. You can see that in the equivalent circuit of transmission line, the unit of inductance, resistance, capacitance and conductance were in something per meter. Now as per the absolute value, the unit of inductance, resistance, capacitance and in the conductance should not be having that meter. So in order to remove that meter from the unit, you have to multiply this with del Z, so that you can see in the right hand side L is equal to H Henry per meter, and into meter, this meter is a unit of del Z. So del is meter and meter get cancelled, and finally you will get Henry. Likewise, you have to multiply del Z with all the parameters in this figure. So now you know the voltage across series components varies, right? Across a series connection, the voltage will be different, and you know here in this particular figure L and R is connected in series. So I am going to write the KVL for that series connection. So I can write del V. Del V is the change in potential, that is equal to minus R into del Z plus the reactance of our inductor is j omega L into del Z, the whole into I. Now you can see a minus sign. This minus sign indicates that the output voltage will be lesser than the input voltage. Okay. Next I am taking del V by del Z by applying a limit del Z to 0. Then del Z tends to 0 is provided in order to avoid the transit time effect. And when you combine del V by del Z, where limit del Z tends to 0, it can be changed into dV by dZ, which is equal to minus R plus j omega L into I. Similarly, you can write the KCL for the circuit, and you know the current will be different across parallel connection. Across a parallel connection, you will be having different different current. So I will be writing KCL for these two components, C and G. So I can write del I is equal, that is the change in current, del I is equal to minus G del Z plus capacitive reactance is j omega C, then into del Z, the whole into V. The same thing which has been written earlier is repeated here. Del I by del Z, then limit del Z tends to 0, minus of G plus j omega C V. And when you remove the limit, I can write it as di by dz equals to minus g plus j omega c. Then I am differentiating equation 1, so I can write d square v by dz square is equal to minus r plus j omega l into di by dz. And di by dz is there in your equation 2, that you can substitute. Finally, you will get d square v by dz square is equal to gamma square v. Okay, where gamma square is equal to R plus j omega L into G plus j omega C. And this is a differential equation, and we have already studied in your mathematical paper that the solution of differential equation is b z comma t is equal to b plus exponential minus gamma z plus v minus exponential plus gamma z. Now in this solution you can see two different terms, where the first term represents the incident wave and the second term represents a reflected wave, and gamma is a propagation constant. Similarly, you can differentiate equation 2, so you will get d square I by dz square is equal to minus g plus j omega c into dv by dz, and dv by dz is there in equation 1, that you can substitute. Finally, you will get d square I by dz square is equal to gamma square I. Again, the solution of this I z comma t, you can write it as I plus exponential minus gamma z plus I minus exponential minus gamma z. Okay. Here it is plus gamma z. Okay, here the solution of I is I z comma t is equal to I plus exponential of minus gamma z plus I minus exponential of plus gamma z. It is similar to the solution of P. Both are same. The only difference is one is for voltage and other is for current. That is all. So where gamma is equal to square root of R plus j omega L into G plus j omega C. Okay. Now coming to characteristic impedance, that is another important parameter of transmission line. We will start with the expression dV by dZ is equal to minus R plus j omega L into I. Now you know the solution for B is B plus exponential minus gamma Z plus B minus exponential plus gamma Z, that is substituted here, divided by dZ. That is equal to minus R plus j omega L into the solution for I is I plus exponential minus gamma Z plus I minus exponential plus gamma Z. Then I am differentiating the first term and second term. Finally, I will get like this: V plus exponential minus gamma Z into minus gamma plus V minus exponential plus gamma Z into gamma, that is equal to this term. Okay. Now, as we said earlier, the first part, this part represents the incident wave and this part represents the reflected wave. Similarly, here also this term represents the incident wave and this term represents the reflected wave. So I am splitting these terms. First I will be taking that of incident wave. So V plus exponential minus gamma Z into minus gamma is a term which represents the voltage for your incident wave, and this is a term which represents the current for your incident wave. Okay, then I will be taking the ratio V plus by I plus, that is equal to R plus j omega L by gamma. Then you know what is gamma. Gamma is equal to square root of R plus j omega L into G plus j omega C, that you will substitute here. And finally you will get V plus by I plus is equal to square root of R plus j omega L by G plus j omega C, which is equal to Z naught is your characteristic impedance. This is an important parameter of transmission line, and Z naught is known as characteristic impedance because it consists of the primary or characteristic constants of transmission line. You know this R, L, G and C are said to be the primary, or in other words characteristic constants of transmission line. That is why this Z naught is called as characteristic impedance. Now what I am going to do is I am going to take the second part of the previous equation, that is the part which represents the reflected wave, or otherwise the wave which is traveling back from load to generator. So that is this one. I am taking it from this. Okay, this. Okay. So I can write sorry V minus exponential plus gamma Z into gamma is equal to minus of R plus j omega L I minus exponential of plus gamma Z. Then I am taking V minus by I minus is equal to minus of R plus j omega L by gamma, and gamma you know it is square root of R plus j omega L into G plus j omega C. Finally you will get Z naught is equal to V minus by I minus is equal to minus of square root of R plus j omega L by G plus j omega C. So this is another expression for Z naught. Both the expressions are same. The only difference is here you will be having a positive sign for Z naught, and here you will be having a negative sign for Z naught. Then the question is why there is a negative sign. Now here you can see a generator and a load, and what happens is the incident wave is moving from the generator towards the load. It is moving away from the generator. And here you can see the reflected wave is moving away from the generator and moving away from the load and towards the generator. I repeat, the reflected wave is moving away from the load and towards the generator. Since it is moving towards the generator, what happens is it will receive more energy from the generator, and this negative sign implies that the reflected wave is receiving energy from the generator. Here it is written, that is the negative value of Z0 in equation B indicates that the wave in the sense the reflected wave is receiving energy from the generator. And that's all in this video. Thank you.